Good morning, everyone. Thank you for coming to my presentation. Today, I will talk about Douglas-fir CLT, which is obviously an innovative engineered timber product for New Zealand. So in the last 4 years at the University of Canterbury, we've done significant amount of research to understand basic properties of Douglas-fir CLT, as well as developing engineered solutions to have more efficient use of Douglas-fir CLT in a building system. So this presentation was also prepared by my colleague, Dr. Thomas Lim, who recently joined School of Forestry from the US. He has a very strong background in wood product development, manufacturing and processing, as well as timber engineering. So my presentation will have simply 3 parts. First, I will give you a brief introduction of CLT, including some numbers and facts of global CLT production, and a brief introduction of CLT manufacturing process and CLT product standard in North America, and 2 recent CLT buildings using mainly CLT for structural application. And then I will talk about the Douglas-fir CLT research, a number of projects at University of Canterbury, and then wrap up my talk with some conclusions. You probably are quite familiar with this different engineered timber product, so they can be used to build multi-story mass timber buildings. So glulam, LVL, they are very strong and stiff, and they can be used for panel type of application, as well as beams and columns. And CLT is relatively new. It was developed by Europeans in early 1990s. In the last 3 decades, however, CLT has gained significant popularity in the global construction market. According to Forest Product Annual Market Review, from the United Nations. Note that this review was published almost 2 years ago, before the pandemic. At that time, the report shows in 2019, the global production of mass timber panels, primarily CLT, was estimated as 1.4 million cubic meter. By 2025, it was forecast to more than double. In 2020, annual global CLT production is predicted to exceed 2 million cubic meter. But again, we don't have the exact number now because of the pandemic. In 2020, the global CLT production capacity is estimated at 2.8 million cubic meters. But that also includes CLT panels used for industrial application. For example, CLT panels can be used for industrial matting for for example, oil or mining business. I know that if you look at CLT application for buildings, Europeans and North America produce almost 90% of the CLT. In Australia and New Zealand, we produce 7% of CLT for building applications. This table shows a list of major CLT producers in Australasia, in Europe, and in North America. I know that in North America, most of these companies started to make CLT product not a long time ago. And that's mainly because in the last decade, there was a huge demand for CLT product for building applications. And then these companies started to invest in CLT manufacturing. CLT can be treated as a type of jumbo plywood. Instead of using thin veneers, CLT consists of sawn timber pieces. So this short animation shows how CLT is made. Starting from sawn timber as laminations, applying adhesive, and press different layers of laminations, then form the solid panels, then deliver to construction site to form the structural skeleton. So it is a very efficient engineered timber product, and particularly they can be prefabricated and they can be assembled on construction site in a very efficient way. So this flow chart shows the CLT manufacturing process. We start from timber drying and do proper grading for laminations, do trimming, finger jointing to form longer pieces, and do proper planing. Some companies may do edge gluing, but some don't. Then surface gluing we must do, and then lay up different laminations or different plies through cold pressing process, either by mechanical press or vacuum press. We can make large size CLT panels and then do the final finishing, then deliver to construction site. In North America, manufacturers follow this standard, APRG 320, to manufacture performance-rated CLT product. This standard has been proved by the US and Canada and was developed by APA, the Engineered Wood Association, based in Tacoma in Washington State. So the basic lamination property essentially is for dry surface use only. Make sure the moisture content in lamination is low. This is similar to structured timber application for buildings. We need to keep timber dry. And the purpose of this product standard is to ensure consistent product quality and reliability. And the standard also specify dimensions and tolerances, performance criteria, test method, and quality assurance process. And also for structural engineers, the product standards specify design properties for selected grades. And the standards include most of commonly used softwood species in North American's construction market. So this long list shows different grades of CLT with different layups or recipe. Pretty much following these recipes, the manufacturers will be able to provide CLT product with the specified grades. So for different species, for example, if we want to make CLT product that will be accepted by North American's market, but we're using New Zealand grown Douglas-fir or radiated pine, so we can follow this alternative path to make CLT product that will be approved by North American market. So the standard also provide two sections here, 8.4, 8.5, to show how the other species or imported species can be used for CLT production in North America. From the structural point of view, CLT is a timber version of concrete slabs. So these CLT panels are prefabricated and they can be delivered to construction site and using mechanical fasteners, steel brackets. Construction team can quickly assemble these panels to form walls and floors and roof structures and quickly build a CLT building in a much more efficient way compared with light timber frame construction technology. So I want to show you two buildings recently finished, one in Christchurch, one in Auckland. So the Christchurch building used CLT as the floor panels, and the Auckland building here used CLT for most of the structural components, including walls and floors and roof structures. So this is a really good example to showcase how CLT can be efficiently used for this multi-story, large-scale mass timber construction. Next, I will talk about a number of Douglas-fir CLT research projects at the University of Canterbury, with the purpose to assess New Zealand-grown, New Zealand-made Douglas-fir CLT product using New Zealand-grown Douglas-fir species. So we sourced Douglas-fir timber from South Island, and these timber all had the SG8 grade, and we also asked XLAM at that time in Nelson to manufacture 3-ply, 5-ply, and 7-ply CLT panels for us. And these panels have various lamination thickness, and we've done extensive research to evaluate CLT, Douglas-fir CLT basic material properties, working on innovative connection solutions to connect Douglas-fir CLT product. And also we developed innovative shear wall structures, mainly for Douglas-fir CLT buildings to resist high seismic load. So this slide shows the screw withdrawal test, and you notice that we are using high capacity self-tapping screws. They are made out of hardened steel with very high yield strength, 3 times stronger than normal structural steel. And this particular testing is to understand withdrawal properties, because these long screws often are used in CLT construction to rely on its withdrawal capacity to transfer load. We also developed new type of hold-on solutions for CLT wall structures to resist earthquake load. In this project, we install screws with different installation angles, and we also tried different repair strategy to explore the possibility of retrofitting CLT, Douglas-fir CLT structures after major earthquakes. We also tried these large steel dowel connections in CLT, again used as a hold-on connections to resist earthquake load in CLT shear wall structures. And you notice that these type of connections are able to resist high load, and also it can dissipate a lot of energy because these steel dowels have bent and timber has been crushed significantly, which means a lot of energy dissipation occurred in these connections. We also worked on this wood carpentry joint to understand how these joints can effectively transfer shear load between CLT panels. And in practical project in Christchurch, engineers have specified these type of connections in CLT buildings. We also worked on large-scale wall structure testing with the purpose to develop low-damage Douglas-fir CLT wall systems for seismic design for New Zealand CLT buildings. This is a currently ongoing research project, again on Douglas-fir CLT wall solution. We now introduce steel link beams into coupled Douglas-fir CLT wall systems, rely on steel link beams to dissipate more earthquake energy, and we can protect Douglas-fir panels in major earthquake event. So we know for timber, it's very difficult to repair if they've been damaged significantly after major earthquakes. So we believe Douglas-fir CLT is a high performance, high value added mass timber product. So it is ready to be implemented in buildings in New Zealand. And overall, we believe Douglas-fir CLT performed as good as other CLT products in Europe and North America. And also we need to work on developing high capacity connection systems to make more efficient use of Douglas-fir CLT in building applications to resist high earthquake load. this is the list of publications coming out of recent Douglas-fir CLT research. And again, I want to thank this research team, my collaborator and my student who spent a lot of effort and time to study Douglas-fir CLT, to explore new applications of Douglas-fir CLT in building design. That's all. Thank you for your attention.